Artificial neural networks, in short, they are known as ANNs. ANNs are the reason why we have LLMs today. ANNs are the reason why we have a lot of complex image processing systems in place. ANNs are the reason why the text processing or analyzing the text data has advanced so much. So artificial neural network, if you take any advanced machine learning or any advanced deep learning application nowadays, or any advanced artificial intelligence application that is running nowadays, or if you heard of any of the application that is looking very, very advanced, is doing highest accuracy or some of the difficult tasks like face recognition, some of the difficult tasks like what you get the output in the chat GPT or text generation, behind everything, the only algorithm, the base algorithm that runs is artificial neural network. This is quite pivotal, and this is a kind of heart of all the advancements that have happened in large language models or machine learning or deep learning or any of the artificial intelligence related applications. Like literally, this is one algorithm that has changed the whole face of machine learning. We're going to get very much in-depth details into this. So what is artificial neural network? Why artificial neural network is quite famous? Artificial neural network is one of the most complex topic. The reason why it is very complex is it solves very complex problems. The applications are very, very complex. So to understand this complexity kind of easily, so what I have done is artificial neural network as it is, if you try to digest it in one go as the whole algorithm in one shot, it will be quite difficult and confusing. So to make it easy, what I'll do is I'll divide it into 4 parts. I'll divide this whole theory of artificial neural network into 4 sub-theories or corollaries. And then once we combine all of them, once we join all the dots, that becomes artificial neural networks final theory. So these 4 points will be very easy to follow. Individually, we may not be able to understand what are these points, but once we combine, like the sequence, that may not make sense individually, but once we combine all of them, finally, that becomes artificial neural network. So let's go through these points one by one to understand in depth of artificial neural network. So point number 1 is a recap of logistic regression only. So this is the logistic regression line. We have class 0 here, we have class 1 here, and then we have this logistic regression line that looks like an S-curve. Imagine if the predicted value is 0.9. What will be the predicted class? If the predicted value is 0.9, that will be classified as class 1. If the predicted value is, let's say, 0.1, that will be predicted as class 0. So is it fair to say we tend to imagine a decision boundary at 0.5? Anything greater than or equal to 0.5 is called as class 1. Anything less than 0.5 is called as class 0. Is that what logistic regression doing while it is giving us which class a particular item belongs to while it is predicting? At the time of prediction, we imagine a decision boundary. We don't get to see that. We don't really draw it. But there is a decision boundary that is sitting at 0.5. Anything greater than or equal to 0.5 is class 1. Anything less than 0.5 is class 0. Isn't that true in logistic regression? Yeah.
Yes, sir. Yes, sir.
Yes, sir.
Now, that's true even for multiple variables. For example, right now I'm talking about one X variable only. What if I have 2 variables? I have X1, I have X2. My target variable Y is now on color. Color blue is 0. Color green is 1. So I have class 0, I have class 1. Class 0 is color blue. Class 1 is color green. Now, even in this scenario, if you build a logistic regression line, that will look like somewhat like this. But I'm not talking about the logistic regression line. I'm talking about the decision boundary. So there will be a decision boundary that will decide this side is class 0, this side is class 1. Is there a theoretical proof for it? Yes. This is the logistic regression line. If you take E to this side, that will be log of this, and so on. That will be the line. And then if you put 0.5 at Y, this will be the line. This is the decision boundary equation that I'm talking about. In fact, we can actually see some data and try to draw the decision boundary. At least until 2 dimensions, we can experiment it. Usually, nobody cares about this decision boundary. We don't draw this decision boundary. But if we try to attempt, let's say this is my data. In my data, on the x-axis, I have age of the employees. On the y-axis, I have years of experience of the employees. So this is x1 variable, this is x2 variable. My target variable is on the third axis, color. Some of the employees did not purchase my product. Some of the employees have purchased my product. Zeros and ones. So I have 3 variables. What are my 3 variables? Age of the employee, which is x1. I have years of experience of the employee, x2. I have my target variable, which is purchase or not purchase. It takes values zeros and 1, 0, 1, 0, 1 like that. This is my data. So by using age and years of experience, I want to predict whether a particular employee, particular person will buy the product or not. If it is class 0, that means the person is not going to buy. If it is class 1, the person is going to buy. Now, if I build a logistic regression line, I will get the predicted values. But if I attempt to draw the decision boundary for this data, can you make a guess where exactly the decision boundary may appear? Can you guess it, where it may appear? Are you thinking somewhere diagonally like this, where this side is class 0, this side is class 1? Is that the decision boundary that may appear?
Yes, sir.
So usually we don't draw it, but to get an idea on the decision boundary, let us try to take this data and try to draw it. So let's go to the code file. I'm going to pass on the code file to you in the chat window. This code file and the data sets, I'm uploading all of them to a particular location, isn't it? In our WhatsApp group, I have given all the material links, etc., etc. From there, you can get it after the session, okay? But right now, I'll provide it to you. Just give me a moment. It's coming up. So I'm pasting this code file in the chat window. Have you got it, all of you? Have you got the code file? This one? Give me a confirmation once you
Yes.
open this. Now, this is a lot of visualization related code. You don't really need to understand, or you don't need to really memorize this code. Once we reach the artificial neural network code, I'll explain, like, it is far below here somewhere. Artificial neural network code will come. This I'll explain parameter by parameter, value by value. I'll make sure that you're understanding everything. But this visualization related code, just for the sake of proving a point, I'm using it. So you just execute it, focus on the output, the code, syntax, and all that. For now, you can ignore. So what I want you to do is import this data set, employee purchase data. We want to take a subset of the data for this particular exercise, and then print the data as it is. Try to visualize the data. What is X1 variable, X2 variable versus target variable, whether the customer will purchase the product or not. And then we will try to build a logistic regression. From there, I want you to draw the decision boundary, build the logistic regression, and then based on that, derive the decision boundary. We're trying to draw it. This is the decision boundary. Is it in line with our expectation? So if everything works well, if you execute the first 4 code snippets, the output that you see will be this one. So the logistic, we are not drawing the logistic regression line here. What are we drawing? Am I drawing the logistic regression line? Does it look like a straight line like this? No. The logistic regression line is an S-curve like this, multi-dimensional S-curve. But what I'm drawing here is a decision boundary that is generated by logistic regression line. It is saying this side class 0, this side is class 1. Give me a confirmation once you have this decision boundary with you in the chat window. Let's give a minute for others to complete this. All right. So that is my point 1. What is point 1? Every logistic regression line gives us a decision boundary. It looks like a straight line that is separating class 0 and class 1. Every logistic regression line gives us this decision boundary that is separating class 0 and class 1. So that is point 1. We are going to make a side note of it. Later on, I'm going to use it. As of now, is it clear? Point 1, is it clear? Understood? Very simple point, straightforward. Yep. Now, let's go to the second point. Later on, I'm going to use this point. The second point. So what happens is, when we are discussing about artificial neural networks, there's a totally new terminology that is used. So usually in the rest of the machine learning and rest of the predictive modeling, we follow a certain terminology. But when it comes to artificial neural network, we follow certain other terminology. Now, if we are not aware of that terminology or the terms that are used here, even though we know the concept, it looks very, very difficult to grasp. It looks very, very difficult to understand and proceed, especially when we are reading any articles related to artificial neural network. It looks very difficult to follow if we do not have the terminology with us. So what I'll try to do is I'll try to give you what is the kind of terminology that is used in artificial neural network. Let's say when we are talking about logistic regression, we expect it to be in a certain format. But the same thing is written or represented quite differently when you're talking about artificial neural network. Both of them are one and the same conceptually, but the way that we represent here and the way that we represent here is extremely different. It almost feels that this is something totally new. So let's see what is the kind of terminology that has been used. What is the new representation for logistic regression that we already know? So what is logistic regression? Y equal to e power beta naught plus beta 1 x1 plus beta 2 x2 divided by 1 plus e power beta naught plus beta 1 x1 plus beta 2 x2. This is the logistic regression line if you have two variables. Now what happens in artificial neural network is there is never a discussion of betas. You will never see something like beta coefficient or beta 1 or beta 2 or beta naught. All these betas will now be called as weights, W's. From here on, we'll be calling betas as W's. W means weight. Y equal to e power W naught plus W1 x1 plus W2 x2 divided by 1 plus e power W naught W1 x1 plus W2 x2. Tell me equation 1 and equation 2. Are they one and the same or are they different? Equation 1, equation 2, are they same or not?
Yes, sir, they're the same.
They're exactly same. Only difference is in the place of beta, instead of using beta, I'm using the terminology W or weight. But when people see this, they may think that what is this weight? How is this weight calculated? Who gives this weight? So the term weight itself is the first confusing point when we are talking about artificial neural network. So next time when you see weight, you have to imagine that's the beta coefficient that we generally see in logistic regression line. Are you with me, everyone? Beta is nothing but weight, weight is nothing but beta. Okay, next time when you see weight, it's just beta coefficient. In fact, it's not even written like this. It's written like this, y equal to g of w naught plus w1 x1 plus w2 x2, where g of x is equal to e power x divided by 1 plus e power x. This is equation 3. Check equation 2 and equation 3. Are they one and the same?
Yes.
I have just represented in a functional format. I have introduced a new function called g of x, which is nothing but logistic function. What is g of 5x? It will be e power 5x divided by 1 plus e power 5x. Similar to that, what is g of w naught plus w1 x1, w2 x2, whatever is x in that place, I have to keep all that equation, w naught, w1, w2. In fact, it's not even represented like this in ANS. It is represented like a graph. The same thing is represented like a graph network. Let's say there is this 1, there is this x1, there is this x2. 1, we can leave it. x1, x2 are connected to y. x1 has a weight of w1, x2 has a weight of w2, and then 1, that means a constant, has a weight of w naught. 1 into w naught, w1, x1, w2, x2, apply g of x on top of it, you will get y. So this is what you will see. This is your logistic regression line that we generally know outside world, but in artificial neural networks, it is represented like this. That means in future, if you have a logistic regression, it will appear like this. x1, x2, y, let's say minus 1.2, let's say 6.1, let's say 1.8. Now this is a logistic regression line. In this logistic regression line, what is the intercept? If I ask you, this is a logistic regression line, what is the intercept value? What will be your answer? What is the intercept value in this logistic regression line that I gave you? Intercept means beta naught. Beta naught is w naught. What is the w naught value here? Minus 1.2. What is the coefficient of x1? There's nothing like coefficient. Coefficient of x1, which is beta 1, which is like w1, that is 6.1. Coefficient of x2, we don't call it as coefficient of x2, we call it as weight of x2, that is 1.8. So what happens is, this is the logistic regression line that we kind of know earlier, but this is the artificial neural network representation, or the terminology that we use going to be this way. We're not going to use the same equation anymore. So it is represented in this manner. Sometimes we write 1 into w naught or directly w naught, doesn't really matter. So that's my second point. My second point is also straightforward. We are trying to find w's, not betas. Like betas are now called as w's or weights. What was point number 1? If you recollect, point number 1 was logistic regression gives us a straight line decision boundary. It gives us a straight line decision boundary that separates class 0 and class 1. And then what is point number 2? From here on, whenever we see weights, or in fact, we are going to see weights everywhere, there will not be any discussion of beta coefficients, but weights are nothing but beta coefficients only. Just due to this reason, that weight is nothing but beta coefficient, a lot of people will get extremely confused. As soon as you open an artificial neural network book, as soon as you read the first page, it says that the weight of x1 is w1. Then we'll be banging our head how this weight is calculated, why x1 was already given a weight of w1. Half of the confusion comes from here only because of the terminology that is used. Make a note of point 1, make a note of point 2. We will combine them later on after proving point 3 and 4. Have you understood these 2 points individually, all of you? Let's wait here before we move on to the next point. Any quick questions? All right then. Let's carry on. Yeah.
Venkat, sorry to cut you. What is the intrinsic pattern? Like, so logistic, it is kind of a logarithm function, right?
Right.
But within this ANN, this W, the behind is what kind of curve?
So what I'm trying to say is ANN that you see here and logistic that you're asking are one and the same. So we should not think that behind logistic, this is logistic curve. Behind ANN, what is the curve? There is no curve. This is the same thing.
Okay.
So this is ANN representation. This is not different from this one. See, look at equation 1 and equation 2. Are they same or not?
Same.
Equation 2 and 3, are they same or not? Check that. This is equation 3. They are same. This is represented like this. If you see this, it means that is equation 3. That is equation 2. That is equation 1. So what I'm trying to prove here is this is your logistic regression line. It is represented like this as a network diagram. Okay. So that means earlier, if I ask you to write a logistic regression line, you used to write, let's say, y equal to e power minus 1.2 plus 6.1 into x1 plus 1.8 into x2 divided by 1 plus e power minus 1.2 plus 6.1 into x plus 1.8 into x2. This is what we used to write earlier. What I'm saying is in the ANN terminology, we haven't yet discussed ANN or anything. What I'm saying is in the terminology of ANN, okay? Instead of beta coefficient, instead of representing the logistic regression this way, we represent it this way. So what I'm saying is this is not different as this one. Let's say this is box 1 is the same as box 2. Okay. Let's say in box 1, if I ask you what is intercept, you'll quickly check here, isn't it beta not value? In box 2, if I give you this as logistration, what is intercept, you have to say minus 1.2. Okay.
Yes, sir.
So I haven't yet proved what is ANN, what exactly is the difference, etc. This is just logistic regression represented using the ANN terminology. So point 2 is quite simple and straightforward. What is point 2? Instead of betas, we are going to call everything as weights. Beta coefficients are now called as weights. Okay. Let's go to the next point. Any quick questions before we move on? Clear? Everyone? On the same page?
Yes, sir.
All right. Now look at this data. You have x1, you have x2, you have the target variable y. How many classes are there in the target variable? The number of classes here in this example. How many classes are there?
3.
So you have x1, one variable is there. You have x2 variable is there. You have the target variable y. If I go to target variable y, how many classes are there in that? Let's say I have zeros, which is blue. I have zeros, which is blue. I have ones, which is green, right? Zeros and ones are there. What about this? Is this a third class? Are we having a new class here? No, this is zero only. So if you see the data in the target variable that you have, is it fair to say you have zeros and ones are there in the target variable? You have all zeros and ones, but they are not clearly separated like the way we have seen earlier. Zeros were one side, ones were another side, but now zeros are here, ones are here, zeros are here. This is slightly a little complex data. Then the usual clear separation is not there. There is a little bit of complexity. Now for this type of data, can we draw one decision boundary that will separate class 0, class 1 in one shot? Is it possible to draw one straight line and say this side is class 0, this side is class 1 in this type of little complex data? If we are, then where will that decision boundary come? Is this correct decision boundary, class 0, class 1? Is that going to work? No, that's erroneous. Can I draw it here and say this side is class 0, this side is class 1? That is also wrong. So when there are multiple decision boundaries, then logistic regression may fail, isn't it? We cannot really find a solid line that is separating class 0 and class 1. When there are multiple decision boundaries, the data is having only two classes in the output, class 0 and class 1. But when there are multiple decision boundaries in the data, you cannot really build one logistic regression line. If you force fit, somewhere the logistic regression line will come, somewhere the decision boundary will come if you force fit, but that will not be a good separating boundary. So logistic regression doesn't seem to be a good option when we have nonlinear or multiple decision boundaries. Logistic regression is not a silver bullet that it will solve every problem in this world. If there is some complexity in the data, logistic regression will fail for sure. For example, earlier we have taken a subset of the data. If I take the full data here, earlier on the x-axis we have age. This is x2, years of experience. This is the target variable y, which is taking values purchase is 0 or 1. This is again 0. So if I look at the data, it looks like this: age of the employee, years of experience of the employee, target variable y, which is purchase or non-purchase, 0 or 1. If you see the target variable, is it fair to say I have only two values in the target variable, zeros and ones? Or do I have three classes in the target variable in this case? Everywhere it is zeros and ones only. Some zeros, sometimes ones. Now, this type of patterns, is this possible? When age is less, years of experience is less, most of the customers are not buying the product. When age is slightly high, years of experience is slightly high, most of the customers are buying the product. When age is too high, when years of experience is too high, most of the customers are again not buying the product. Does it really happen in the real world? These kind of patterns, do they exist? These type of patterns, do they exist?
Yes.
When age is less, years of experience less, most of the customers are not purchasing the product. Maybe in a particular band, people are buying something like health insurance. When age is very less, years of experience very less, most of the people do not buy health insurance. Maybe in this level, when age is in this range, years of experience in this range, most of the people buy health insurance. When age is really high, years of experience really high, already they have health insurance. Something like home loan, age less, years of experience less, people do not take home loan. In a particular range, people take home loan. When the age is really high, years of experience really high, they already have or they don't need home anymore. Do you think these type of patterns exist in the real world? They do, isn't it? Let's say something like a car. A car is for a particular segment. If somebody's income is very less, they may not be able to buy that car. If someone's income is very high, they will not buy that car. Let's say if you take, let's say, Swift car, only a particular segment of income people will buy. If the income is quite less, they may not buy that car. If the income is too high, they may go for a better, version of the car or slightly higher version of that car. So these type of patterns do exist in the real world. Now, if I fit a logistic regression line, can you guess where will the decision boundary come? The decision boundary to separate class 0 and class 1, where is it going to appear? So if you try to put the decision boundary here, this side is class 0, this side is class 1. Now, if you put it here, let's say if you put it here, this side is class 0, this side is class 1. Is that a good decision boundary? We can't really decide where is the decision boundary going to come here because this data is a little complex. Logistic regression, we can say that it's going to fail. We can force fit. If I try to force fit, let's say if I take this whole data and if I try to check this whole data and try to go ahead and build a logistic regression model, that nobody will stop us if we are building a logistic model x1, x2 versus y. This is sufficient. It doesn't mean that that's going to be a great logistic regression model. So if you try to fit a logistic regression line and draw the decision boundary, can you see where is the decision boundary appearing? If you observe closely, then you will be able to find out where exactly is the decision boundary. Where is it? Where is the decision boundary?
Left one.
In the left near the origin, it says that this side is class 0, this side is class 1. Tell me honestly, is this a good separating decision boundary? Is it separating class 0, class 1 accurately?
No, sir.
Is it really classifying class 0, class 1 accurately? No, not at all. This is not a good decision boundary at all, isn't it? So that's my third point. Logistic regression fails in case of either multiple decision boundaries or non-linear decision boundaries. Logistic regression is not the only classification algorithm that is used in this world. There are some places where logistic regression fails utterly, and this is one example. When I say fail, the accuracy of the model is quite less. It is just slightly better than a random guess. If you guess randomly, what will be your accuracy? It will be 0.5%, which is like 0.5, which is like 50%. We are getting slightly better accuracy than 50%, which is far, far worse. Logistic regression fails in case of multiple or non-linear decision boundaries. So the first point was logistic regression gives us a straight line separating decision boundary between class 0 and class 1 if they are separable. The second point was there is no more discussion of betas, we call them as W's only. The third point is when there is complexity in the data, you have zeros here, you have ones here, you have zeros here, then a single decision boundary, a straight line, you cannot draw a straight line to separate class 0, class 1. That means logistic regression fails in case of multiple decision boundaries or non-linear decision boundaries. Make a note of point 1, point 2, and point 3. And then once I prove point 4, we'll combine all of them. Let's go to the next point. Since a straight line decision boundary is not working, so let's come up with a solution here. Let us suppose if I take only this region of the data. So right now I have x1, I have x2, I have the target variable y. This is my data that I have, x1, x2, and y. In this data set, what I'll do is, I'll take a region, I'll take a portion of x1, x2. Y is also there. So I'll take a portion of x1, x2, y. Let me call that as region 1. In region 1, do you think logistic regression is going to work?
Yes, sir.
We have seen it. Where will the decision boundary come? The decision boundary appears somewhere here. So what I'll do is I'll take only this region 1 data where x1, x2, and y is there. In that, I'll build a logistic regression model. Let me call that as model M1. Then from there, I'll take the intermediate output of that model. From that logistic regression, I'll take the prediction, store them in intermediate output 1. Let me store them in H1, which is the intermediate output 1. The H1 is the data from the logistic regression model 1. These are all the predicted values made by the logistic regression model M1. Then what I'll do is I will take one more region. Let me take this as region 2. In region 2, you have x1, you have x2, you have y also. Observe region 2, all of you. In region 2, focus on region 2. You have x1, you have x2, and y is also there. Yes or no? If I build a logistic regression line there, is it going to do a good job of separating class 0 and class 1?
Yes, sir.
If I build a logistic regression line there, yes, it will definitely separate class 0 and class 1 for sure. So let me build a model there. Probably that will be the decision boundary if I build a model. So what I'm going to do is I'll build model M2. From there, I'll get the intermediate output and I'll store it in H2. So intermediate output H1 has been given by model 1. Intermediate output H2 will be generated from model 2. What are H1, H2? These are all just the predicted values from model 1, predicted values from model 2. Then what I'll do, I'll use H1, H2 to predict the value of Y. So what is the process that I'm following here? Usually you have to predict directly the target value Y using X1, X2. Have we already tried it in the previous exercise? Directly predicting Y using X1, X2. Have we tried it? We tried it. Did it work? It did not work. So what are we doing right now? We are using a portion of X1, X2, a region of X1, X2 to predict H1, a region of X1, X2 versus Y to predict H2, and then we are predicting Y using H1 and H2. So originally you have to do this X1, X2 versus Y. Originally you're supposed to do this, but this did not work. Now we are doing this. So instead of building one logistic regression line, how many logistic regression lines are we building right now? Total, how many logistic regression models? X1, X2 to H1, that is one. X1, X2 to H2, that is another one. H1, H2 to Y, that is another one. Total 3 logistic regression lines are built. Why are you complicating this process? Why can't you simply directly do it? Why are we complicating? Because the data is complex. We cannot build a simple model for a complex data, expect it to perform well. So I'm complicating this process because I want to have good accuracy. If you want to have good accuracy on a complex data, you have to build a complex model. So instead of building one logistic regression line, we are building 3 logistic regression lines. That means earlier you have to find only 3 weights, W0, W1, W2. Now you have to find 3 weights related to this, 3 weights related to this, and 3 weights related to this. Total 9 weights we have to find to build this model. For example, in our data, directly one logistic regression. Have we tried directly X1, X2 versus Y? Have we tried it already? Have we tried it? Directly predicting the target variable by using only X1, X2 directly? We have tried. Where did the decision boundary come? Here. This is absolutely wrong. So what we will do is in our data, we will take region 1. In this region, if I build a logistic regression line, where will the decision boundary appear? We have already seen in exercise 1, it comes somewhere like this. Now what I'll do is, I'll take region 2. Let me call that as region 2. Can you imagine this as region 2? In region 2, if I build the logistic regression line, where will the decision boundary come? Let me call this as H1. Where will the decision boundary appear? It will appear somewhere here. This is called as H2. Now the original problem statement is X1, X2 versus Y. But now that you have H1, H2 created, the predicted values of model M1, predicted values of model M2, the problem statement has been now transformed from this space. What is the original space? X1, X2 versus Y. From this space, we have transformed this problem statement into which new space? Tell me what is the new space we have transformed this problem statement into?
H1, H2 versus
H1, H2 versus Y. Instead of calling this problem statement as I am predicting Y using X1, X2, you're going to call this as I'm going to predict Y using H1, H2. Now we are not really sure whether H1, H2 have the ability to predict Y unless until we draw and we check and see. So let's do step-by-step procedure. First, what I'll do is, initial model, we have already built this on region 1. That was our first exercise. So I'm going to build model M2 and then create 2 intermediate outputs. What are these 2 intermediate outputs? Inter 1, predicted values by model M1. Intermediate output 2, predicted values by model M2. So if you want to see how these intermediate outputs appear, they just look like predicted values of a logistic regression, the numbers between 0 and 1, 0 and 1. So intermediate output 1, H1, intermediate output 2, H2. Now what I'll try to do is, I'll try to draw H1, H2 versus Y. So this is the new problem statement, your transformed space. The original space, the diagram would appear like the one that we have seen here. In the original space, the diagram will appear like this. But in the transformed space, this is now H1, H2 versus target. Now tell me, do you think H1, H2 have the ability to classify Y? This is H1, this is H2, this is Y. There are some zeros, there are some ones, there are some zeros. Overall, may not be 100% accuracy, but overall, can you separate class 0 and class 1? Is it possible? Do you think H1, H2 have now the ability to classify class 0 and class 1?
Yes, sir.
Yes.
Is it possible? That means you have to draw one straight line that is separating class 0 and class 1. Maybe most of the class 0 should be one side, most of the class 1 should be one side. Remember, it has to be a straight line decision boundary. It has to be either like this or like this or like this or like this. It cannot be a curvy. So if that is the case, where will that decision boundary come? Can you make a guess? Where exactly it appears? The decision boundary? Where will that decision boundary come to separate class 0, class 1? Most of the class 0 will come one side, most of the class 1 will come another side.
The diagonally when the red dot
So-
starts, yeah.
Is that what you're thinking? A straight line?
Yes, sir.
This side is class 0, this side is class 1. So that
Yes,
means
sir.
if you're saying, if I build a logistic regression line, H1, H2 versus Y, and if I try to derive the decision boundary out of it, that should appear somewhere here diagonally. Let us test it, whether it our intuition is really true. This is a decision boundary. So what is it trying to say? H1, H2 have now the ability to predict the target variable Y effectively. The model H1, H2 versus Y has huge accuracy. Do you agree? H1, H2 versus Y has 94% accuracy, 94% of the cases, except these cases, it could predict perfectly. Yes or no?
Yes, sir.
So finally, we have done the right classification. Finally, we have done the accurate classification. So this is the original space, which is X1, X2 versus Y. From this space, we are transforming this problem into H1, H2 versus Y. So in that space of H1, H2, we have class 0, class 1 separable. One decision boundary was sufficient. So what we have done mathematically, if you see what is happening, what is this magic that is happening mathematically? Imagine this is a sheet of paper, a white paper. On that white paper, I have some blue dots on this corner, blue dots on this corner. I have some red dots right in the middle. Then I'll give you a knife. And the rule is you can use the knife and you can only use it once. You can only cut the knife in a straight line, but only once. You cannot cut it twice. Have you understood? You have to separate class 0, class 1. You have to separate blue dots and red dots, but you can use the knife only cut it once. You cannot lift the knife, or you can not cut it twice, or you cannot do a kind of curves. Like if you're using the knife, you have to just cut it like this. How do you separate class 0, class 1? Directly in this space, if you keep the paper as it is, you cannot cut it. You cannot separate them. But if you transform this to a new space, that means hold the paper here. This is a paper, sheet of paper. Hold the paper here, then start folding it. Can you imagine what I'm trying to say? Hold the paper here, start folding it. Then all the red dots will appear at the top. Yes or no? Once you fold the paper, The folded version is H1, H2 space. The original space is X1, X2. In your A4 paper or in your sheet of paper, this is the axis that you have. From that axis, once you folded it, you are changing the reference as H1, H2. Once you fold it, can you cut it at one place to separate class 0, class 1?
Yes, sir.
Yes, now you can separate class 0, class 1, isn't it? Make sense or not?
Yes, sir.
Yeah. So what's happening here is, in this space of X1, X2 versus Y, we are not able to find a separating boundary. We are not able to do the classification. We are transforming it. Using X1, X2, we created H1. Using X1, H2, another portion, we created H2. In that space, we are able to find the separating decision boundary. Finally, we have done the classification. Finally, we have got a good accuracy for the model. Finally. But in the direct space, X1, X2 versus Y, we could not get it. We found it in a different space. We created H1. Have we got any external data? Is it H1? Is H1 and any external data from outside? Have we got it? Let's say a client has given you X1 data, X2 data, Y data. Have you used only this data, or have you got any external data from outside?
Same data, sir.
The
So
same
we
data.
have used X1, X2 versus Y data only to do the classification. But instead of doing it directly, we transformed it into H1, H2 versus Y. So what did we do? We used intermediate outputs to solve the problem of non-linear decision boundaries. Instead of directly predicting using X1, X2, we have transformed it. Using X1, X2, we have got H1. Using X1, X2, we have got H2. From H1, H2, we got the target variable Y. So to predict the target variable Y, you have used H1, H2. But to predict H1, H2, what did we use? To predict H1, H2, we have used X1, X2. That means, is it fair to say to predict Y, ultimately what we have used? Ultimately, we have used X1, X2 only. Y is a function of H1, H2. H1, H2, they are functions of X1, X2. That means Y is indeed a function of X1, X2 only. So to predict the target variable Y, we have used X1, X2, but it was not a direct function. First, there is a logistic function. On top of it, another logistic function. Usually, if the problem statement is simple, that is X1, X2 versus Y, this was sufficient. But the problem statement is complex. From X1, X2, we went to H1. From X1, X2, we went to H2. Using H1, H2, we predicted our target variable Y. So we have built 3 logistic regression lines. So what do you mean by model building? I have built model 1. That means I have to find these 3 weights. I have built model 2, these 3 weights. Model 3, these 3 weights. That means I have built this whole model if I have all these 3 plus 3 plus 3, 9 weights available. So we have manually built this model, created H1, created H2, then created Y. These 3 models, manually we found these weights. Once we go to artificial neural network, what artificial neural network will do is automatically within one shot, it will find all these 9 weights within one go. So neural network is all about finding these weights within one shot. Whatever we have done manually, neural network will do it in an automated manner. That means neural network will automatically build H1, automatically build H2, and then automatically build H1, H2 versus Y, and all those 9 weights will be given to you within one shot by neural network. So the first slide of neural network, usually this is the first slide of neural network. A neural network has input layer. In the input layer, you have the input nodes, X1, X2. A neural network has hidden layer. It has hidden nodes. Earlier in our discussion, I called them as intermediate outputs. There's no concept of intermediate outputs here. Actually, they are called as hidden layer or hidden nodes. Then you have the target variable, Y. Depending on the number of classes, the nodes will vary. So input layer, input nodes, hidden layer, hidden nodes, output layer, it will have output nodes. So that means if you want to build a neural network model, you have to find these 3 weights, these 3 weights, and these 3 weights, these 9 weights. And neural network uses a particular algorithm to find all these weights within one shot. Like the way we have built model 1, model 2, and then model 3, that doesn't happen in the real world. Neural network has a particular algorithm that will find all these 9 weights within one shot. And we have manually divided into region 1, region 2. In our exercise, we have divided into region 1, region 2, and then we built the model. That is not required when we are dealing with artificial neural network. If you give the data, automatically this overall model will be built. Automatically, these weights will be calculated within one shot. The artificial neural network is a model that will help you to solve complex problems. For example, here in our problem statement, you have zeros here, you have ones here, you have zeros here. So how many hidden nodes or how many decision boundaries are required? To solve this problem, we have used 2 decision boundaries. Imagine you have ones again there. To solve this problem, how many decision boundaries or how many hidden nodes are required to solve this kind of problem?
3.
3. Let's say you have zeros here. How many hidden nodes are required to solve this problem? 3 are sufficient. Or to solve it effectively, how many are required? 4. Let us suppose again you have zeros here. You will add one more decision boundary. Again, you have ones here. You will add one more decision boundary. Again, you have zeros here. You add one more decision boundary. You add one more. Again, if you have ones here, again, you add one more decision boundary. Is it fair to say by adding sufficient number of decision boundaries, we will be able to solve any complex problem in this world? Let's say a problem statement is very, very complex. There are so many complexities. To capture all of them, all that you need to do is what? To capture all those complex patterns, you need to add more and more
decision boundaries.
Hidden decision boundary is nothing but hidden node, isn't it? One hidden node. There is only one layer. There's only one hidden layer, but there are multiple hidden nodes. Every hidden node is nothing but in our discussion, we named it as decision boundary. In reality, there is no such concept of decision boundary. There is no such concept of intermediate output. But just for the sake of our discussion, I have introduced them. In reality, they are known as hidden nodes. So neural network or artificial neural network is known as universal problem solver. What is universal problem solver? If you have any data in this world, if there is any complexity in that, any amount of complexity, you can solve it. There is nothing that you cannot solve it by using artificial neural network. If the data is very, very complex, what are you going to do to solve it? If the data is damn complex, what are you going to do to solve it?
We add hidden layers or hidden nodes.
Hidden layer only, not hidden node only. There is only one layer. Don't get confused. There's only one layer, hidden layer. In that, we add multiple hidden nodes. Are you with me? Let's say there's a self-driving car. In that, we want to find out whether it is a car or whether it is a road or whether it is a tree or whether it is some kind of person we want to avoid. If we are building such complex models, in them, we have to add as many hidden nodes as possible. No matter what is the complexity in the data, you can capture that by adding as many hidden nodes as possible. Now, sky is the limit here. Like there is any problem in this world, you can solve it by using ANN. It's not that only you have to use it for complex problems. For example, if the data is like this, there are zeros here, there are ones here. To solve this problem, how many hidden nodes are required?
1.
To solve this problem, how many hidden
No.
nodes are required?
Nothing direct.
There are zeros here, there are ones here. How many hidden nodes are required?
Only one.
Can you
One.
solve it by using logistic regression directly, or do you need hidden nodes? Think about it.
Directly.
Directly using logistic regression, you can solve it if there's a clear separation boundary. Yes or no? So I would say 0 hidden nodes are required. Yes or no? You can solve it directly using logistic regression. We have seen one example, isn't it? Where class 0 is this side, class 1 is this side. You can directly build a logistic regression line. That means you can use this one, x1, x2 directly connected to y. So that means a logistic regression is a special case of artificial neural network, isn't it? What is the special case? A logistic regression is a special case of artificial neural network. This is also an artificial neural network with how many hidden nodes? With 0 hidden nodes or 0 hidden layers. Logistic regression is also an artificial neural network, but it has 0 hidden nodes or 0 hidden layers. So what we are going to do is now we are going to dwell into many more details of artificial neural network, how these weights are calculated, how do you decide how many hidden nodes need to be taken, all those details. As of now, this is usually the first slide whenever you open any artificial neural network lecture or anywhere. Everything starts with this network. Everybody starts saying you have input layer, hidden layer, output layer. But usually the question that comes to our mind is like, what is this hidden layer? What is it doing? Have you now understood why we have to create a new abstraction? Why can't we directly predict y using x1, x2? x1, x2 doesn't have the ability to predict y directly. We have to transform it to a new space. By introducing a hidden layer, we have transformed the problem to a new space. There we are able to separate. Does that make sense?
Yes, sir.
Yeah. So no matter how much complex a particular problem is, no matter how complex a data is, we will be able to build an artificial neural network model and find almost all the patterns that are there in the data without fail. So your hidden layer contains hidden nodes. Those are nothing but a function of hidden node, or hidden layer is a function of input layer or input nodes. Your output is a function of hidden nodes. That means your output has been predicted by using input x1, x2 only. So that is the basic intuition behind artificial neural networks. We will now go to neural network algorithm. What is a neural network algorithm? All that you need to do in the real world is you have to supply the data. You have to supply the data, And you also
Venkat
need to
sir,
supply number of hidden nodes. I'll give it point. So you have to supply the data. You have to supply the number of hidden nodes. Once you supply the data, once you supply the number of hidden nodes, the artificial neural network will find these weights. Once these weights are found, you have the model ready, isn't it? What is the model? All these weights together. Once you have this model ready, you can supply the values of X, you can get the predicted values of Y using that model. Now, how do you know how many hidden nodes are required? By looking at the data, we have to experiment, we have to discover it. For example, if the data is very simple, less number of hidden nodes are required. If the data has a complexity, hugely complex, then more number of hidden nodes are required. There's only one layer. Hidden layer is single layer, but more number of hidden nodes are required in that. For example, data is too simple, but you have used too many hidden nodes. Let's say data is simple, you require only 5 hidden nodes. 5 hidden nodes are required, but we are not able to check that from the data. There's no way we can get an idea. So while building the neural network model, I have given 50 hidden nodes. What will happen if I give 50 hidden nodes where 5 hidden nodes are required? In that case, what will happen? Think about it. If there are too many hidden nodes that were configured while building the model, the data is simple, but I have given too many hidden nodes. What may happen?
overfitting.
Overfitting, isn't it? That means the model will look good on your training data, but it is trying to find even the smallest of the smallest patterns. So it will lead to overfitting. Overfitting means your train accuracy will be, let's say, 98%. Test accuracy will be somewhere around 70%. Then if the model is overfitted, what will you do? You're not going to leave it. You're going to reduce the number of hidden nodes. Are you with me? Let's say when you realize that the model is overfitted, you reduce the number of hidden nodes. This is model iteration 1. M1 model was built, but we ignored that model because it is overfitted. So now I'm building model M2. This time I have built the model by using only 2 hidden nodes. If I build the model by using only 2 hidden nodes, what will happen in this case? 5 hidden nodes are required, but by mistake, I'm using only 2 hidden nodes. Model will be built, but what will be the problem with this model?
Underfitted.
So this model will have very less accuracy, isn't it? You will get the model, but it will have very less accuracy. That is known as underfitting. What is underfitting? The model is not even showing good accuracy on the data set that we have used for building. That means 2 is very small. Model underfitting means train accuracy itself will be very less. Then you try to increase the number of hidden nodes. Usually we do not use lesser number. Usually a good idea will be always use a higher number of hidden nodes, iteratively reduce it so that your stopping point will be maybe after 4 or 5 iterations, you will have the final ANN model where you have the highest train accuracy and matching the test accuracy. That is when you finalize. Maybe in 2-3 iterations, you'll be able to build the best ANN model for a given data set, which will have the highest train accuracy and the matching test accuracy. So you have to supply X, Y, number of hidden nodes, and you have to build multiple models and choose the best one that suits for your data. Once you supply X, Y hidden nodes, neural network uses one algorithm, neural network algorithm, to find out all those weights that we are talking about. Yes, please carry on. Somebody was about to ask a question. Please carry on.
Venkat sir, I have
Yeah.
2 questions.
Hmm.
So first question is, how do we find the number of hidden nodes if we don't want to conduct experiments? Through experiment, we can find whether it's underfit, overfit, and find the middle one. But without experiment, looking at data when data is very big,
There is
so
no way. There is no way.
okay,
Because here, right now, I am drawing the data x1 versus x2 versus y. Here, in our data set, there are only 2 variables. In reality, there will be n number of variables. In reality, the data is like 1000 dimensions, 2000 dimensions, or 5000 dimensions. There is no way without actually building the model, checking whether it is overfitted or underfitting. There is absolutely no way we can find. Let us suppose I have the data. Maybe I'm a data scientist. I have been building artificial neural network models from past 30 years. Even then, by looking at the data, nobody can decide what is the optimal number of hidden nodes. Okay, you have to build the model, check whether it is overfitted or underfitted, and then you have to do a couple of experiments, and then you have to finalize the model. The best part is, let's say if the optimal value of hidden nodes is 8, usually what happens is 6, 7, 8, 9, 10. Usually they tend to give similar results. It's not like a sharp point that just below it is underfitting will happen, just above overfitting. This doesn't happen. It's a huge range of values. It may give the same results, but we have to make sure that we have
so
to
again,
build.
are we doing again gradient descent or approach or grid search approach to find the best hidden layer, number of hidden layer? What is the approach then?
Just now we have discussed the approach. Let us suppose I have given you a data set. Okay, I gave you a data set and I asked you to build an artificial neural network model. Let's think it like step by step. Okay, Let us
Mhm.
suppose I have given you a data set, okay? And I asked you, Rishi, please build an artificial neural network model. Or you realize that this is a complex data set. Even if I build a logistic regression, I'm going to fail. Or maybe you have checked that you already built an artificial neural network model, or you have already built a logistic regression model, it failed. So it's a complex data, it's an image processing data where you're predicting or classifying the objects. So for this, what is the approach that you're going to follow? First, you go ahead with slightly higher number of hidden nodes, okay? Model M1.
Okay.
So let us suppose for this particular problem, the optimal value of hidden nodes was 8. But we do not know that. There is no way by looking at the data, it is humanly impossible. By looking at the data, this is the optimal number of hidden nodes. Nobody can tell that. 8 is the optimal number, but as of now, you do not know. So you build model M1. Maybe by looking at this data, if you are an absolute beginner, you have not solved this problem, absolutely never in the past, then it will be a bigger experiment. If you have been solving these type of problems, these type of data you have been handling, last time when you build the model, it worked with, let's say, 12 hidden nodes. Maybe you'll start somewhere nearby that. Maybe I'll go with 16 hidden nodes. But 8 is optimal value. With 16 hidden nodes, what will happen?
Overfitting.
Overfitting will happen. That means you will observe on the trained data, you have, let's say, 96% accuracy. On the test data, you have, let's say, the model M1, you have built this model with 16 hidden nodes. And then you got train accuracy of 96%. Let's say test accuracy of, let's say, 62%. And what will you do next? Are we going to finalize this model?
No.
No, this is
No.
overfitted. Obviously, you will not do it. So
Yeah.
model M1. So there's some learning here. Are you going to go higher than 16 or are you going to try lower than 16 now?
Lower.
Definitely you'll try lower than 16. So let us say you have built model M2. Let's go slightly much lesser than 16. Maybe this time you tried with only 2 hidden nodes. Optimal is 8, but you have tried with 2 hidden nodes. What will happen in this case?
Underfitting.
Underfitting means the train accuracy itself will be 60%. Test accuracy, we don't even see that. Even if you see it somewhere nearby that, it will come. Then I know that there is something wrong. There is a chance for this data to show higher accuracy, but now I'm getting too poor an accuracy. 2 did not work. Underfitting happened. 16 did not work. Overfitting happened. Now what are you going to try? Are you going to try randomly some other number or what will be next best guess?
Midway.
Somewhere
Middle of this.
to middle of this, maybe something like what 9 you have tried. Then you will get the train accuracy. Then you will get the test accuracy. Let's say train accuracy is 90%. Test accuracy is, let's say, 89%. Usually if 8 is optimal value, 8, 7, 8, 9, usually they tend to give the similar values. Then maybe around this, we can do a little bit of 1 or 2 experiments and find the best model, which is giving the highest accuracy on train data, matching accuracy on the test data. Like this, maybe in 2, 3, or maybe 4 or 5 iterations, you will be finalizing the model.
Okay.
Later on, actually, there are methodologies. Later on, there are methods to find the best value by not changing the whole architecture of this model. But as of now, at this level, you can understand this as the basic way of finding the optimal number of hidden nodes. Makes sense?
Yes, sir. And sir, one more question. This might sound silly.
This one, have you understood?
Yeah, this I got it.
Okay. Let's
can
just
you...
wait. Any follow-up questions on this methodology, everybody? Given a data set, how do you build an artificial neural network model that is perfect? It doesn't happen in one go. Iteratively, we have to discover that model. Is that point understood, everybody?
So Venkat sir, is that doing multiple iteration is called hyperparameter fine tuning?
So this number of hidden nodes, okay? Number of hidden nodes is known as a hyperparameter, okay? So we are fine tuning this hyperparameter. That is right.
Okay, sir.
Finding that, doing these experiments, finding the optimal value. So number of hidden nodes is one of the hyperparameter. So this is known as hyperparameter fine tuning. That's right. Yeah, carry on.
Regarding this weights calculation, I used to hear that this will be a feed forward and back propagation model from your previous videos.
So which we haven't discussed yet. That is known as neural network algorithm, which is our next point of discussion. How these weights are found by using neural network algorithm, which I'll explain in depth, which is coming up actually. Just hold on to that question. Yeah, carry on, Rishi.
Yeah, so in the previous slide, you were sharing one more. Yeah, here.
Yeah,
H1 and H2. These are the two logistic two models.
Right.
2ML.
Right.
So
Logistic regression model.
Yeah, if we are deploying logistic in H1 and logistic in H2, for both X1, X2, or input variables are same.
No, different regions. Remember, The name of the
Okay.
input variable is same. If you remember, we have created
Okay.
h1. Let's say if you take this one, the sample is different. This is x1, this is x2.
Got it.
Yeah,
Okay, yeah.
makes sense.
Yeah.
This
Yeah,
is
yeah.
also x1, x2. This is h1 is created, h2 is created. So basically, what is artificial neural network? It is a layered logistic regression model. That means you have x1, you have x2, you have h1, you have h2. h1 is a logistic regression, h2 is a logistic regression, and then you have y, which is also a logistic regression. So we can call this artificial neural network as layered logistic regression, which is like one layer of logistic regressions, on top of it another layer of logistic regression.
Okay, got it.
Yeah.
Thank you.
So whatever we have done until now is just the intuition I tried giving you, how exactly this artificial neural network works. Now what we are going to discuss is, once you give the data of x and y, once you give the number of hidden nodes, neural network follows an algorithm, neural network algorithm. So now I'm going to explain you the theory behind that algorithm. So we have understood the intuition, then we will go to the algorithm theory, then finally we combine all this to experiment on a case study. Okay. But before I get started with this algorithm, are there any quick clarifications that we need to make quickly on whatever we have discussed until now? If you have any questions, quickly, please let me know.